In this video, I want to review exponents and square roots. Begin by just taking a couple minutes and thinking about these first two questions. What is an exponent? What does that tell us to do mathematically? And what is a square root? And what does that mean mathematically? So take an opportunity to pause real quick, think about these things, think about what you might know, and then unpause and we will discuss. So if we're looking at this example, we have 3, let me make that pen a little bit bigger here. So if we have 3 with that little 2 above it, we say that's 3 to the second power. The 2, that little number up top, this is our exponent. And the 3 down here, this is what we call the base. Right, so what exponents do is exponents, they tell us how many times to multiply a base times itself. Base times itself. So for example, this 3 to the second power, 3 to the second power is just 3 times 3, which we would say is 9. 2 to the fourth power is 2 times 2 times 2 times 2. And if we multiply that out, 2 times 2 is 4, times another 2 is 8, times another 2 would be 16. So whatever that is, we just multiply it times itself, however many times that is. If we have things together in there, for example, we might have something like 3x. If we have that times itself twice, we're going to write that entire thing out. So that'd be 3x times 3x. And this is kind of a unique situation. Students get tripped up a little bit here sometimes because we really need to remember at this point that 3x actually means 3 times x. So what we got is just a long string of multiplication. This is really 3 times x times 3 times x. And so if we were to simplify this, we can also rearrange multiplication however we want. It doesn't matter what order things go in. So if I think of this as 3 times 3 times x, which we can do, we get 9x squared. So be careful with that. Anything that's in the parentheses that's squared or raised to another power, we need to take all of it and multiply it that number of times. Square root, this symbol right here. The symbol itself, this is what we call a radical. So if I have the square root of 9, for example, we could call this thing with that symbol, the radical symbol, and the number under it, we could call this a radical expression. And if we were to simplify this, or to just, I guess evaluate might be a better word, the square root of 9 is 3. And what square root really means is, well, I always think of it as a question, right? So when I see, for example, the square root of 9, I think to myself, what number times itself is equal to 9? Right, so what number times itself is equal to 9? And it's going to be really helpful if you can remember these nice perfect squares, as we call them. So the numbers like 4, because that's 2 times 2. 9, 16 is 4 times 4, 25, 36, 49, 8 times 8 is 64, trying to make sure I don't miss one, 81, 100 is 10 times 10, 11 times 11 is 121, and 12 times 12 is 144. If you can remember those, that will really help, because the square root is like the opposite of squaring, right? It like undoes this. So the square root of 4 is 2. The square root of 25 is 16. I'm sorry, I went to the last number. Square root of 25 is 5. The square root of 49 is 7, and so on and so forth. that'll really help in general and with kind of what we're going to be doing here in just a minute. So a couple things with exponents, simplifying, just a couple practice. This is, again, I would try these on your own, pause the video, and then come back to this and take a look at the answers. So 3 to the third power, this is 3 times 3 times 3, which is 27. Go over to part B. Remember, this is where we have to take both of these things twice, and we could expand that if we wanted to, and we could think of this as 4x squared. Next, same idea, but we're just doing it 3 times now. So 3x times 3x times 3x, and that would be equal to 27. The 3 times 3 times 3, x times x times x is x cubed. 7 looks pretty horrible. Let me fix that a little bit here. There we go. xy, don't let just the variables confuse you. It's still the same thing. It's going to be xy times xy. And again, xy is connected by multiplication as well. So this is really x times y times x times y, or x squared, y squared. Moving on. We often want to simplify radical expressions, and this means leaving as little as possible under the radical. So for example, let's look at this expression, the square root of 128. So the process for this is to factor it, and we want to factor it ideally in such a way that that one of our factors is a perfect square. So for example, I can find factors of 128. One factor pair would be 64 and 2, right? 128 is equal to 64 times 2. By writing it in this way, I haven't changed anything. I haven't changed the value of anything. But this does allow us to simplify this expression. So one thing that might not be as intuitive is that we can split this square root up into as many pieces as we want, meaning once we get these factors, anything that's multiplied together, I can split up. So I can split that into the square root of 64 times the square root of 2. And this is really nice because I know the square root of 64. The square root of 64 is 8. There's not much I can do. I can't simplify that square root of 2 anymore. Square root of 2 is prime, and it is not a perfect square, so I'm left here. We also don't need that multiplication symbol. We don't need that dot. In algebra, when we put 8 square root of 2, that multiplication is implied. So this would be our final answer. All right, if we simplified the square root of 128, it is equal to 8 times the square root of 2. Some practice problems down here. So I would maybe recommend just trying these first. So write these on a separate piece of paper and then come back and look at the answers. I'm going to talk through a couple of these kind of quickly, so then you could come back and check your work. I do want you to notice that these can be done in different ways. It's not always going to work out perfectly. If you don't get to the right factors right away, it can take a few extra steps, but that's okay. And in this example A, we did find that right factorization that's going to work out really nicely. So I've got 75 is equal to 25 times 3. We split it up just like we did in the other example. 25 is a perfect square. Our simplification would be 5 times the square root of 3. In B, this one also worked out pretty nicely. If we split 90 up into 9 times 10, we can take the square root of 9 is equal to 3, and our final answer is 3 times the square root of 10. This one needed a little bit longer to kind of exemplify how this might look like if you don't get that nice perfect square right away. So if I looked at 270 and I said, well, I can factor that into 27 times 10, that's true, but neither of these is a perfect square. I'm going to need to do some more factoring and some more rearranging, and that's what I did here. So 27 is 3 times 3 times 3, And then I factored the 10 as well into 2 times 5, right? So 270, we can say this down here would be the prime factorization. So we factored it down to all the prime numbers. Now, once we have those, we can rearrange them however we want, because again, order doesn't matter in multiplication. And what we're really looking for is pairs, right? Because if I'm going to split this up into other square roots, anytime I've got a pair, so 3 times 3, right, when I multiply that out, so 3 times 3 would be 9, and then the square root of 9 is just 3, right? So anytime I've got a pair, like this pair of 3's, I'm going to separate them, and when I take the square root, you just end up with 3. And then anything that's left over, this 3 times 2 times 5, we just multiply them back together, and they're going to stay under the radical, square root of 30. Final example, this is another one that worked out nicely, but depending on your original factor pair, it might not. So just kind of take a look at that answer. And I did kind of add one little extra here because first examples didn't look at variables. So if there's a variable under there, like this x squared under the radical, we can treat this exactly like we do numbers, right? If I factor 60, that's 4 times 15, and I factor x squared, that's just x times x. It's still a pair. We don't know what x is, but it doesn't matter because anytime I have something squared, that x squared, I have this pair, the square rooting undoes that square, right? They're opposite functions. So the square root of 4 is 2. The square root of x squared is just x. And then I'm left with my 15 still under the radical. And final topic here is not leaving a radical in the denominator. So if I have, for example, if I have this 4 over 5, what I want to do is I want to remove that radical from the denominator. And actually, I'm going to kind of backtrack and erase this a little bit here so we can kind of think about it from scratch. And I don't want to change the value of this expression. And I want this to stay the same. I just want to make it look different. I want that denominator to not have a radical in it. So the one thing I can do to make something look different but mean the same thing is multiply by 1. Right? I can always multiply by 1 and still have the same value, the same number. And so we might think about, well, what does it look like to multiply by 1? Okay, so we're going to think about some things that are actually equal to 1 that we might not think about. So if we just think about any two numbers, for example, 3 divided by 3. 3 divided by 3, that is equal to 1. What about if we just have variables, though? What if I have x over x? I don't know what x is, but it doesn't matter. What is that? That's still just 1, right? Anything divided by itself is just 1. Similarly, if I have the square root of 5 over the square root of 5, that's still just 1. And this is the idea that we're going to use in order to simplify and get that radical out of the denominator. So if we multiply this by that square root of 5 over square root of 5, I'm multiplying by 1, right? Square root of 5 over square root of 5, this is equal to 1. I'm not changing anything. And I multiply, we go straight across. So if I go across top, 4 times the square root of 5 is just 4 times the square root of 5. I can't simplify that anymore. On the bottom, though, just like we did above when we were able to separate radicals, we can also combine them. So the square root of 5 times the square root of 5 is the square root of 25. And this works out really nicely because we know the square root of 25, and that's just 5. So this is the thought process, right? If whatever this bottom number is, if I multiply by that over itself, I will end up basically canceling out that radical in the bottom and simplifying our expression. And there's a couple more examples here. And you will start to notice a pattern as you go through and do these expressions as you simplify. And the one thing that additionally that we could do is, in a case like this, part D, we can actually do some of the division and simplify a little bit further. So through the normal process that we did above, we would end up with this. And since I've got 12 divided by 6, right? This is still just multiplication up top, so it's all multiplication and division. I can do this division, 12 divided by 6, and get the final answer of 2 times the square root of 6.